Okay, so I'll continue from previous session. This is about power consumption. So what is given here? B1 is 100-watt bulb. So let's mark this one is a 100-watt bulb, and B2 and B3 both are 60-watt bulb. This is 60-watt bulb, and the other one also is 60-watt bulb. Question is, what is the okay? Now, if these are the outputs, it can also come in terms of brightness. Which order the outputs are? We can calculate, but can we just answer logically what will be the sequence of output? Now, if I compare, now when two are connected in series, we know already which bulb gives more brightness between B1 and B2. The one with the lower voltage will have greater brightness. The reason also is simple. What is the reason here? First, look at series combination. When they are connected in series, see, their power ratings are when voltages are equal. When they are connected in series, voltage is not equal. What is equal? Current is equal. So when they are connected in series, I is same. So power consumption will be proportional to I square R. I being same, power consumption is proportional to R. Unlike parallel combination. So here, which will have higher brightness? So B2 will have more power consumption compared to B1. So lower wattage consumes more power in case of series connection. Now we compare B2 to B3. B2 has a voltage lesser than 250. B3 has full voltage of 250. So B3 will be brighter than B2 or more power consumption. So that's the order. Very simply, we can get this order. But this also we understand from here when they're connected in series, the more power. Now, we also did something. Suppose we have a battery here. This battery is EMF and it's an internal resistance R. And R is a variable resistance. If it is something, so what should be the value of R so that power consumption in R is maximum? That's a maximum power consumption condition here. So we assume since R can vary, so we'll take as X. R is X. This resistance here is X here. So what is when would it consume maximum power? That's what we need to find. Power consumption will be equal to I square R. I square X is the power consumption. But as X keeps increasing, I keeps decreasing. So that's why there is a maximum here. If one this is a product of two quantity, as one quantity increases, other decreases. So current is a function of X also. So how do we find condition for maximum power? I need to express power as a function of X here, resistance. Then only you can differentiate dP by dx is equal to 0. How do we express power as a function of X? Okay, I write in terms of X, I will be equal to, so these are fixed quantity. I is equal to E divided by R plus X. E is a constant, R is a constant. So I square X, so this power, I get power as a function of X. And when I differentiate, I get the value of X, which is equal to R. So what has to be the variable resistance so that power consumed in that variable resistance is maximum? When this resistance is equal to resistance in rest of the circuit here, equal to resistance in rest of the circuit. And when we come to a combination, this is also mixed grouping. And just quick recap of this kind of mixed grouping here. What we notice, they're all identical batteries, and they're N batteries connected in series. N batteries connected in series. So we make one module of N batteries all connected in series. And if they are connected in series, you can replace them with one equivalent battery. And when the escalating, equivalent battery will be equal to EMF will be equal to NE, and resistance also will be equal to NR. So, and now all are in parallel. How many modules which are in parallel? M modules in parallel. So it becomes equivalent to something like this, battery NE and NR. And like this, how many are there? M of them are there. This is how mixed grouping is. So this is NE and this is NR and all of them. And how many such of them? M numbers in parallel. If what is the final equivalent EMF? All batteries are identical now. When batteries are identical, equivalent EMF in case of parallel combination is equal to EMF of either battery. So equivalent EMF is equal to NE, and equivalent internal resistance will be equal to all internal resistance connected in parallel. Since m of them are there, it will become equal to NR by M. So this whole arrangement is equivalent to a battery of Ne and internal resistance being equal to NR by M. So what is the condition for maximum power consumption in R when R is equal to NR by M? That's the condition for maximum power consumption. Okay, that's how we arrange. So now NR by M, so N is number of cells in the row, divided by number of rows is equal to capital R by R. And this is very easy to remember. There's no need to memorize this formula if you understand the simple logic. And this is not very important. We can, and once we have this number, and what would be the current flowing here? Current will be basically internal resistance and external resistance are equal. Current will be equal to E equivalent by 2R or equal to NE by 2R. Equivalent EMF is N into E. Now I'll do one more question. I'll do in a slightly different way, because this is something I think perhaps a more general way, and it gives you understanding to solve a different variety of questions. So this question had come, but I will make it a little more different. Let's say this resistance is R1, which is fixed, and this resistance is equal to R2. These two are fixed, and there's a battery EMF. EMF battery also is fixed. What is the question here? Question is, what should be the value of R so that power generated in R is maximum? Okay, something similar, but it's not a single resistance. They're connected like this. It's odd combination, and you'll come across a result which is pretty interesting. Okay, so how do you find here? So let's say current flowing in this resistance is equal to I here. Yeah, I need to find I. I is a function of R. So I will write power as a function of R, and then I have to differentiate. That's how I need to do. Let the current in the rest, this will be R, and this current is I. If this is I, and then this will be equal to I1. How much I1 will be equal to? So I1 into R2 will be equal to IR. So what is I1? So I can write I1 is equal to I into R divided by R2. And if this is a current here in this circuit, what is the current flowing through R1 here? Current flowing through R1 will be sum of these two. So I can write that current flowing through R1 will be I. This will be equal to I plus this term. So it will become R2 plus R divided by R2. If I add those two up. Okay. So, and but we have additional condition. The total potential drop should be equal to E. So I can write this condition. What is E equal to? E equal to potential drop across R1 plus potential drop across small r. So potential drop across R1 will be equal to I into R2 plus R by R2 into R1 plus IR. So basically I get I as a function of R. You can easily get I as a function of R. I could write this one also. If I take I as common here, it becomes equal to R1 into R2 plus small r divided by. So I get I as a function of R, and then I can get power also as a function of power. Power will be equal to I square R, and then I calculate dP by dr is equal to 0. I'm not doing all the steps, but what I'm trying to tell you, what is the final result it gives you? It gives you R is equal to R1, R2 divided by R1 plus R2. Now, can someone think of what is the significance of this result? And we have seen this kind of result somewhere else also. So can someone recall what is this result looks similar to? And where have you come across and what is the significance? You can do these steps. I'm just giving a hint about this. Does anyone recall? What does this indicate here? We have seen something similar here. Anyone recalls that one? And if you are not able to recall, I will slightly change this question. In place of R, suppose I put a capacitor here. And if I have to find what is the time constant for charging of this capacitor, To find time constant, I use a concept of tau also. I use RC, R equivalent C. What is the R we take here? What is the R equivalent in case of RC circuit? We take R equivalent. How do you find the R equivalent? R equivalent is equal to resistance between terminals of the capacitor. Distance between terminals of the capacitor by shorting the battery, which is come equal to same. So even here also I find what has the value of R such that power consumption, that resistance becomes maximum. This resistance has to be equal to equivalent resistance in rest of the circuit. But how do you calculate rest of the circuit when it is complicated like this? Rest of the circuit between these two terminals, we have to define which 2 points between the end points of the resistance R by shorting the battery. So that's a very, very general way of finding condition for maximum power consumption in a given resistance. This is very similar to equivalent resistance in case of time constant. Okay. Something about fuse connection. So the large building, so this is also a question which have come. So any building, see basically how does it function? You have supply source, and supply source, so you have to visualize. It's an AC source, but it's still let's try and understand it. The supply source maintains a potential difference of 220 volts. So you can imagine it is not a correct one, but this is something what is necessary to understand such kind of question. So you have so there's a kind of wires running, and the difference is 220, and we can connect different appliances across it. So I can connect a fan here, we can connect a heater here, and all those things are connected. And whenever all those bulbs is here, so whenever we connect any particular appliance, it will draw some current I1. This will draw some current I2, and this will draw some current I3. So as we switch on more and more appliances, the current which is drawn from the source is equal to sum of current drawn by all appliances. Okay, and this is how this functions here. So when we design a fuse, the current, what we do not want short circuit. What is purpose of fuse is to avoid short circuit. And short circuit is something when our resistance close to zero gets connected. When resistance close to zero gets connected, it will consume huge amount of power, and it will lead to melting and fire. Okay, but when a resistance, this is called short circuit, a very small distance gets connected, very small distance draw huge power, and it will draw huge current also. Suddenly the current drawn will become very large. So what is the fuse here? Fuse here is which disconnects, which melts as soon as the current reaches the current which can be drawn when all appliances are switched on together. Fuse current is equal to summation of current drawn by all appliances put together. So if we do so, we can calculate current drawn by each one of them. Power is given, voltage is given. We can calculate current drawn by 15 bulbs plus current drawn by this bulb, current drawn by fan, current drawn by heater, all put together becomes the capacity of the fuse of the building. Is summation of current drawn. So what is capacity of fuse? And it is measured in terms of ampere. So fuse capacity is summation of current drawn by all appliances. So even if all appliances. Okay, some more circuit solution kind of question. Wherever switches are there. So there's a standard way of solving question. Let's understand what is the standard way of solving question involving switches. A circuit has an emitter connected here. Its reading is same when switches S1 and S2 are closed or open. Right now it is shown as open. When it is open here, basically how is the current flowing? Current is flowing in this part only. It has certain reading. So let's look at two circuits. We can draw this first circuit is like this when it is open. This is what the current is flowing here. And emitter reads whatever current is flowing into this. Whenever nothing is mentioned, we assume ideal emitter. So what will be the emitter reading? It will be equal to current, which will be equal to 1.5 divided by the total resistance. This will be equal to 350, 450. So this is 1 by 300 amps is the reading of the emitter. That's what I say when both are open. When we close both the switch, then what will happen? So this switch also is closed, and the switch also is closed. You notice what is the effect of closing of this switch? If I close this switch, this point and this point resistance is 0. So these two are 0 resistance and 50 resistance are there in parallel. So effectively, this no current will flow through this. This also becomes the resistance between these 2 points for this entire part becomes 0. So this is my circuit here. And still, this current is if the reading is same, it means this current is 1 by 300. So what is the value of R we need to calculate? If this value, I think we'll just tell you the steps here. If this value is, this is 1 by 300, we know what is the potential difference. The potential difference, this resistance is 100, will be equal to 1.3 volts. If this potential is 1 by 3 volts, we know the remaining potential difference has to be happened here. So this potential difference will be equal to 1.5 minus 1 by 3 volts. So I can calculate this potential difference. Hence, I can calculate this current I also. Once I calculate this current I minus 1 by 300 becomes current here in this circuit here, I dash. And once I have this current I dash into R is equal to 1 by 3 volts. If I equate, I get the value of R. So this is a way how to find this value resistance R. So any question involving operation of switch, there are two circuits. One before switch operation, one after switch operation. That's all I say. Okay, now understanding of something like how does voltmeter and emitter function. To make this understand, I've taken a simple example and I had done it earlier. So suppose that two resistors are connected like this and current is flowing and potential difference between point B and C will be equal to 6 volts. Very easy. This will be 3 volts and this potential difference is 6 volts. So if you have a potentiometer connected between point B and C, if you use a potentiometer and if we measure potential difference between B and C, it will read, 6 volts. It will read 6 volts. Now, if I connect a parallel resistor, large resistor, this is 6 ohms, this is 6,000 ohms. When I connect, what would be the potential difference B and C? Potential difference will change. And between B and C, equivalent resistance, if I calculate, this comes equal to equivalent resistance. It reduces, of course, it needs to reduce here, it becomes less than 6. And if we calculate, potential difference comes something like this. Equivalent resistance, again, I calculate value of current here. And after calculating current, I can calculate potential drop here. And so what has happened when I connected this? See that what has happened. If I have connected a very large resistance, there's a very small change in the potential equivalent resistance here. Resistance has decreased here. If this resistance has decreased, equivalent resistance for the circuit has decreased, and equivalent resistance circuit decreases means current will increase. The circuit has changed. So current has gone up here. More current will flow now than what was flowing earlier. As current increases here, this part here earlier the potential drop was 3 volts. As the current increases, this potential drop across AB, VAB will increase. And as total potential drop has to remain same, VBC will decrease. That's what will happen. And if the change in resistance is small, all these changes are small here. So as this resistance is very large here, changes are small. If this resistance was smaller, the changes also would have been large. So more we connect anything in parallel, it alters the whole circuit. It changes the current, it changes the potential. So what will happen? So there's a potential difference. Now, if what is ideal voltmeter? Ideal voltmeter is when resistance is approaching infinity, change will be very small. Okay. So this is ideal one, which is like a potentiometer. No change will happen here. Okay. So what does voltmeter do? Voltmeter. So if we have a voltmeter here, this voltmeter connected, and suppose this voltmeter had a resistance of 6 kilo ohms. This voltmeter reading would have been, what would have been the voltmeter reading? Not 6 volts. This voltmeter reading would have been 5.998 volts. So voltmeter, even if it is it's non-ideal one, it always measures true value of potential difference across the point it is connected. It still measures true value. Okay, but true value may not be same as the potential difference before voltmeter was connected. It measures correct value, but this value is not the same as it was before the voltmeter was connected. So whenever voltmeter and ammeters are there, we always assume or they show the correct reading for the circuit they are connected. Emitter voltmeter give the true value of current or voltage, though it may not be same as the value before emitter or voltmeter was connected. Okay, voltmeter is connected like this. Okay, so they are pretty simple questions here. I'll quickly run through. A voltmeter is connected across 400, but this resistor here is not an ideal voltmeter. It will give the reading between, it will give the true potential difference between 2 points. It will not give the true potential difference as existed before voltmeter was connected. It will give the potential difference between 2 points after the voltmeter was connected, 30 volts. This is true reading, which means this potential difference is 30 volts, which clearly implies that effective resistance between these 2 points is equal to 300 ohms. I can find the resistance of voltmeter here and we can solve this question easily. Okay. First part, it gives you value of resistance. When I connect across 300 ohms also, again I can solve, easily solve. It is equivalent to connecting. What will be the reading here? Reading would be equal to potential difference between these 2 points. So voltmeter always gives you true value of potential difference, not the, yes, what is the doubt you have?
So here we take the voltmeter to be non-ideal because of the value they give, 30 volts.
Yes, it's clearly indicative. It's clearly indicative of that. Yes. Okay. Let's look at one more interesting question. I think this question I had not done earlier. A voltmeter and emitter are connected in series across a battery of EMF E and negligible resistance. Okay, something like this. What is this one? This is emitter, and this is a voltmeter. And all emitter, voltmeter, all are nothing but devices which have resistance. It has resistance connect, and it also has a dial gauge. So that's all. So this is resistance RA and this is RB. It is connected across E here. Okay. What would be the reading of emitter? So basically, let me finish the question. What question says here? Afterwards, so they have connected. So of course, this emitter voltmeter, it will have certain readings. And afterwards, we connect a resistance R parallel to voltmeter. So this voltmeter here, we connect a resistance R. And after we connect this here, the reading of emitter as well as voltmeter will change naturally because the circuit has changed. What is given is connected. The reading of emitter increases to 3 times while that of a voltmeter reduces to 1/3. So what is RB by R ratio? So what is the ratio of this resistance? And let's understand what this question means here. Okay. So initially, what is RA reading? Let's try and understand what does RA reading mean. See, when we connect, there's some current flowing through in the circuit I. Reading of emitter is I value. So what is emitter reading? A is equal to I, which is E divided by RA plus RB. Now question is, what is voltmeter reading? Voltmeter reading. What does voltmeter reading show? Voltmeter reading always show potential difference across the ends it is connected to. So what is the potential difference across the two ends of the voltmeter? Voltmeter is equal to I into RB. That's the reading of the voltmeter. That's the reading of the voltmeter is given. Now coming to this case here, what it says the reading of emitter increases to 3 times. First of all, does it make sense why the reading of emitter should increase? Moment I connect a resistance in parallel, overall effective resistance of the circuit is decreasing. As the resistance decreases, current has to increase. So this current becomes equal to 3I. Okay, what is this current become 3I? Let's look at this, see how easily we can solve this question. And if this is 3I, part of it will go here, part of it will go here. Earlier, when the current was I, it had a reading of V. Now, this reading, RV reading is how much? Now, V dash, reading of RV. What is reading of RB? Is equal to its potential difference. Okay, potential difference across these 2 points. And this reading is IRB by 3. That's reading, which implies this current here is I by 3. That's what it means. Current in the voltmeter has become 1/3. That's why the potential drop also become 1/3. Hence, reading also become 1/3. If this is 1/3 and this is 3I, what is the current flowing through this part? 8I by 3. Now, do I get this ratio here? Very easy. What is the ratio here? Both potential drops are equal. R into 8I by 3 is equal to RV into I by 3. I get my answer. So this is a fairly interesting question, and I think we have not done it earlier, and it's a pretty good question. See that if you understand this question, it gives you a very good grasp of functioning of resistor, emitter and voltmeter. Right, we come to something called a rheostat. What is a rheostat? Rheostat is something, it has a sliding contact. I think, yeah, something like this. Rheostat is a resistance, but we can keep shifting the point of contact. When I keep the contact here, the resistance, which is part of the circuit, becomes 0. When I shift towards right, resistance will keep on increasing. So the questions, variable resistance, we show something like this also. So in this question, suppose something like this given, if they may also ask the question, what will be the minimum and maximum reading of the emitter? The emitter reading will be maximum when the rheostat resistance is 0, and emitter reading will be minimum when rheostat resistance is 30. So it's a variable resistance, and such kind of question we can easily solve. Coming to V2, I'm not going through a derivation kind of thing. You understand what VT stone is. It's very simple. You done multiple question, and we can use VT stone, balanced VT stone. Balanced V stone, a typical application is meter bridge. So this is arrangement for meter bridge. And here also, this is something like a jockey, which you can slide on the meter bridge wire, and jockey is connected through a galvanometer, and this is a kind of circuit here. So this also is a VT stone bridge. Along one diagonal, across one diagonal we connect a galvanometer. Across other diagonal we connect a battery. That's a VT stone. And in balanced state, when current to galvanometer is 0, ratio of resistances are equal. That's a VT stone. That's in case of meter bridge. So if it is a uniform wire in galvanometers connected through and something, okay. So what is the key point we come across here? R by X is the resistance, ratio of resistance here. R by X has to be equal to resistance across AC divided by resistance across CB of the wire. If wire is uniform, it will have certain resistance per length, and balancing length is L. It becomes equal to lambda L into lambda 100 minus L. That's the principle of meter bridge. It works on VT stone bridge principle. Okay, so let's look at some simple questions based on this. In experimental set of meter bridge shown in the figure, null point is obtained at a distance of 40 centimeter from A. So we obtain a null point, 40 centimeter. So we know what does it imply here. If a 10 ohm resistor is connected in series with R1, so this is state 1. We obtain 40 ohm at a distance this. Now something else is done here. What is done here? If a 10 ohm resistance is connected in series with R1, so we connect another resistance. Resistance how much? 10 ohms. We connect 10 ohm resistance in series. This resistance will increase. If this resistance will increase, this part of resistance also should increase. Balancing point must shift towards leftwards. Null point shifts by distance of 10 centimeter. So where would the null point shift? First of all, be clear, null point will shift towards left. So null point becomes this 30 centimeter. This is second step. Third, what resistance should be connected in parallel with R1 and plus 10? So I'll redraw this part here. See what has happened to this part. Earlier it was, this was resistance was R1 here. So this earlier the resistance was R1. We connected 10 ohms in series here. So it becomes something like this. Third part, what is asking is, what should I connect in parallel to both? Parallel to both means how it is the third resistance connected? Third resistance R is connected like this. Such that null point shifts back to its original position. How do we solve? We can solve this question in slightly circuitous way also. But if it shifts back to original position, what does it mean? So it means if it shifts back, this chart has not been changed. If it shifts back to original condition, it means resistance, effective resistance should be equal to R1, initial resistance. Then only it will shift back to the original condition. So I can write this equation. What is the equivalent resistance now? R1 plus 10 into R divided by, or something like this you can solve. So basically I'm explaining so that we understand effect of adding resistance in parallel series. When we add in series, resistance will increase and the corresponding balancing length on that side also will increase. And connecting in parallel, it decreases resistance, it decreases the corresponding length also. Coming to this question, we have done these questions earlier, but I'm just repeating so that we have refreshed our memory. In this case, Vita bridge, here wire is not uniform. So what has to happen for balanced condition? If this is R1 and this R, so balanced condition, ratio of resistance should be equal to not the ratio of length here. It has to be equal to ratio of the resistance here. So what is given here? R is something like this. So first let's understand what it means. It means if I write L is distance measured from one end. So this L is distance measured from here. This is direction L here. So what is given? dr, resistance for a small piece, is some k times dl divided by root L. This is how the resistance is. So if I have to find resistance between 0 to L, so what will the resistance from 0 to L? I need to integrate from 0 to L. That will become resistance between 0 to L. KL dl by root L, and which becomes equal to 1 by 2k root L. This is resistance between 0 to L. That's pretty simple. Now question is very simple afterwards. If two equal resistances are connected, shown in the figure, this resistance is R, this also is R. So which if two resistances are equal, balanced condition, what does it imply? R by R has to be equal to resistance between AP divided by resistance between PB, has to be equal to 1. Okay. Since resistance is known as proportional to distance, I can also write this is equal to 1. We can also write resistance between AP divided by resistance between AP plus resistance between PB, which is resistance between AP divided by resistance between AB. AP divided by AB has to be equal to similar ratio compounded divided by 1 divided by 2. Basically, it means the resistance balancing length will be such that its resistance is half of the total resistance. I put these values now. RAP will be equal to A to P, length is L, 2K, root L, and divided by resistance between AB, L is equal to 1. I get the value of L from here. So root L is equal to 1 by 2, or L is equal to 1 by 4, 25 centimeter. A similar question. So there are resistance given. Here, this is something, it involves resistivity as well. So here, a wire on the meter bridge, radius changes linearly from R to 2R, from left hand to right hand. Where should be? Now again, two resistances are equal. So whenever we connect here, basically again, this resistance of this part has to be equal to resistance of this part here. And this is the balance point. Similar to previous question. So here also, basically this resistance should be half of the total resistance. That's what we had right now. So again, resistance between AP has to be equal to half the resistance between AB. So all I need to do, I need to find the resistance for a varying cross section. So let's do that. So if I look sideways, this is how it looks like. This is x is equal to 0. This is x is equal to L, which is 100 centimeter. And radius is varying from small r to 2r. Or if I say it is varying, if I take the surface has some angle alpha. So what is tan alpha equal to? If I write tan alpha, the surface make an angle alpha. Alpha will be equal to tan alpha delta y by delta x. It will be equal to r by L. Okay. So what I need to do to calculate resistance here, again, if I want to calculate resistance from x is equal to 0 to x is equal to L, or I want to calculate resistance right from this end to this end, we need to divide into several small pieces like this. Then only, why I'm dividing, cross section is changing with distance x here. If I make x to be very small, then cross section can be treated to be constant. To make the cross section constant, we divide into infinite small pieces and we take the resistance of a random piece. And how are all such pieces connected? All such pieces, same current is flowing through all pieces are connected in series. So I'll calculate dr, add up all the dr. So what is the dr calculation here? Okay. If I take a random piece, let me calculate resistance of random piece here. This at a distance coordinate x, dx. I need to know the radius rx here. So what is will dr be equal to? Dr is equal to rho into L by A. So rho L by L could rho into dx into pi rx square. So what is Rx here equal to? R is equal to Rx is equal to R plus X tan alpha, or this can be written as R plus X tan alpha is X by tan is equal to R by L. So that's basically R 1 plus X by L. So once I have Rx, I substitute into dr. So what is the resistance from 0 to x? Resistance from 0 to x will be integration of 0 to of dr 0 to x. You can find whatever you can find resistance. So this question is also to help you understand how to calculate resistance of a conductor of varying cross section. Okay, these are simple questions of position interchange, how it will happen here. So this is what we have done for today up to meter bridge. So tomorrow I am going to cover the remaining part of current electricity. Remaining part, what does remaining part mean? Remaining part is potentiometer and also RC circuit. So those are two things I'm going to do tomorrow. And we'll finish.